Bismillahirrahmanirrahim. ELE424 Analog Electronics 1 Diode Applications. We are now at the last topic under Diode Applications, which is Zener Voltage Regulator. This is from video pack 2 and this is the fourth video if we consider all the previous videos under different parts as one video for each of the video. I am Wan Fazlida Hanim Abdullah. I am from the Faculty of Electrical Engineering, UiTM. Okay, topics covered. We will cover first, as usual, we'll do the introduction, we'll cover the basic concepts, practical info, and then we'll do the Zener Diode model series network, and we'll have a look after that to the voltage regulator. Introduction to Zener Diode. Okay, always, as previous videos, when the screen goes yellow like this, I'm doing a recap, and when I do a recap, I'm either going to do a revision from a previous topic from ELE424 itself, or from an earlier concept in circuits, or even science that you studied in high school. Okay, recap for the diode reverse bias and breakdown from earlier topics. Okay, if you remember, when we did our bridge full wave rectification, just an example of an application. Okay, we know that diode is conducting when forward biased when it is in the direction of positive current flow. So if I were to follow this circuit schematics that I have on the screen, okay, if it's V in, if this terminal is more positive than the lower terminal, then the current will flow, and current will flow where current is in the direction of positive current flow for the diode. So this diode will be in the positive current flow, and this diode will be forward biased. Okay, but this diode on the left here is going to be reverse biased. So we know that diode is non-conducting when reverse biased, or when it is in the opposite direction of positive current flow. Okay, so the blue ones will be forward bias and the yellow ones will be reverse bias, and we want it to be reverse. When it is reverse bias, we do not want it to allow current flow. But we also know that if the reverse bias applied voltage is strong enough, i.e. to the point that it exceeds the peak inverse voltage, the diode can break down and allow current flow even though it is in reverse bias. So yes, we say that these diodes will not allow current to flow because it's in reverse bias, but if the push is strong enough, these diodes can break down. In this diagram, in this circuit that we covered earlier, we did not want it to break down. Okay, so if you look at the current voltage device characteristics, you will see that from 0 here, it will go up to forward voltage. If we apply the diode bias, the bias across the diode to be more than the forward voltage, it will turn on. But as it goes to negative reverse bias, up to a certain point, it will break down. So in our application, we do not want it to break down. So if possible, we want this value V breakdown to be as negative as possible. But in some cases, the breakdown voltage is a fixed value that is intended to be reached, i.e. we want the diode to break down at the voltage value that we expect to happen when it is reached. Okay, in this example I gave you earlier, we do not want it to break down. But what I'm saying now is that in this topic is a topic where we want it to break down. When a device breaks down, it doesn't mean that it is damaged. It simply means that it is allowing current to flow when it is reverse biased. So this is an example, still an IDVD device characteristics curve, but here maybe the breakdown is at a smaller value, and this value here is intended. If you follow my laser pointer, this value could be something smaller. It could be 3 volts, it could be 5 volts. It is designed to break down at that value. Okay, as opposing to the case of the breakdown in the full wave rectifier, half wave rectifier situation, we do not want it to break down. So we use devices whose breakdown voltage is as negative as possible. But in this chapter of Zener Diode Regulator, we are handling diodes that we want it to break down. Okay, so what is a Zener diode? Okay, here on the screen is the device characteristics that shows ID versus VD, which is diode current versus diode voltage, and it shows that in the negative voltage region, okay, it breaks down at VZ. So a Zener diode is intended means we want it to, intended to break down at a precisely designed reversed biased voltage VZ. Okay, that's VZ there. Zener breakdown are intentionally designed to break down at lower voltage levels. I'm repeating myself, this word intentionally, yeah. So Zener breakdown is a result of tunneling of carriers across the junction. So a Zener diode is one that is designed to safely operate in its Zener region, biased at Zener voltage. Okay, means that it is safe for operation. It does not mean that it breaks down, then therefore it is damaged. It simply means that it is allowing current flow in the reverse bias. So the steep IV curve, this one is steep, which is good. This steepness indicates that the diode in the breakdown region can lock the voltage at a specified value VZ when it breaks down in the reverse bias, just as it locks a value at VF when it turns on in the forward bias. Okay, so here the forward bias locks at VF, and here the Zener breakdown, it locks at VZ. So still introduction. Okay, I usually have this slide on practical information on Zener diodes using simplified terms. It's not so much for the exams, but it's there so that you understand that these devices that I'm talking about here are practical devices. A Zener diode acts like a two-way gate to current flow. Okay, in the forward direction, it's easy to push open, say only about 0.7 volts, just like standard silicon diode, maybe 0.6 volts. In the reverse direction, it's harder to push open, maybe, and it requires a voltage equal to the Zener's breakdown voltage, VZ. So the breakdown voltage can start from 1.8 volts to higher values at fixed values, so depending on the model. So for example, if I go online and I want to buy a Zener diode with a breakdown voltage 3 volts, I can find this 1N5225B, okay, or what do I have on screen here? This is a 9.1 Zener diode, which is IN4739A, and the power ratings can vary anywhere from 0.25 to 50 watts. So this is a 1 watt Zener diode. And this below here is a 3 volt Zener diode. Okay, and these are the prices. Okay, they're pretty cheap. This one here is 20 cents per piece. Okay, if you buy in a bulk of 250 units, and the one above here is almost 10 cents. If you buy in a bulk of 5,000 units. So I'm not trying to sell this to you. I'm just trying to tell you that they are sold online. People do buy them because they do find ways to build practical circuits. Okay. So Zener diode model series network. So now we know that the Zener diode are intended to work in the reverse bias mode. It is intended to work in the breakdown region. Okay. Basic concepts, Zener diode models and notation. So in the forward bias on the screen here, it shows that it turns on at 0.7 volts for this particular model that is on the screen. And here between 0.7 and VZ, okay, it is like an open circuit because it is non-conducting. And at VZ, it breaks down and it becomes the voltage across it as VZ. But if you notice, when it is in forward bias, the positive terminal is the higher terminal, which gives you 0.7 volts. But when it breaks down, it is at the negative terminal that VZ is indicated as positive. Okay. So if Zener diode is operating in forward bias region, the voltage drop is positive at the P side. Current flow is in the direction of the arrow in the symbol. So this arrow is like that way. Okay. In between forward bias here, to turn on voltage and VZ, diode is an open circuit. So this is what I was saying just now. Okay, when the diode enters a Zener region, the voltage drop is positive at the N side. Can you spot the difference? It's quite important when you redraw your circuits and put in the models. Okay, whether it turns on at VZ or whether it turns on at the forward bias. But usually if it's a Zener diode, we design it to operate in the reverse bias. Okay, so current flow is in the opposite direction to the arrow in symbol here. So the current will flow from the negative terminal to the positive terminal. Okay. So just like the turn on voltage, the diode is locked at VZ once it enters Zener region. Okay, now let's have a look at replacing the circuit in the model. Okay, let's say we have here a simple circuit, V in, R2, and this Zener diode VZ. Okay. And let's say just for example, we have a forward voltage of 0.7 volts and a Zener voltage of 3 volts. Okay, so it cuts the x-axis at -3. So when it is in forward bias, let's say for example, I use V in equals to 5 volts and take note of the notation of positive negative here, because the positive terminal is connected to the positive terminal of the Zener diode. So we are forward biasing the Zener diode. Can it function? Yes, it can. Okay, because the forward voltage is 0.7 volts and it is in this 5 volts is enough to turn on the voltage, then it will turn on and the Zener diode will have a voltage drop across it 0.7. But if I apply 0.1 volts, just like the other silicon diode before this that we had with switching diodes, the signal diodes, if it is less, then it is not enough. Even though we have the positive terminal connected to the higher potential, but it is not enough to turn it on because it is not enough to overcome the forward voltage. So the Zener diode becomes an open circuit. Now if I reverse bias it at 1 volt, okay, if I reverse bias it at 1 volt, it is still an open circuit because firstly it is here, somewhere here. It is in, if you follow my laser pointer, it is, even though it is in reverse bias, but it has not reached the breakdown voltage, which is 3 volts. So it will still be non-conducting. But let's say I apply 4 volts here. Okay, 4 volts with the positive terminal connected to the negative terminal of the Zener diode terminal. So if I have 4 volts and it requires only 3 volts to turn on, okay, this Zener diode will break down, assuming that this voltage of resistances allows it to break down. Okay. Okay. So this is what we have. Okay. So example, let's have a look at Zener diode in series circuits. Okay. So given, let's say we have a circuit that has a forward voltage of white LED here to be 4 volts, a silicon diode. This is a silicon diode, which is 0.7 volts. VZ, which is 6 volts. Okay, notice how the Zener diode is connected in the circuit. It is already connected in reverse bias. Okay, it is in the opposite direction to positive current flow that is expected into the white LED. Okay, so the breakdown voltage for this Zener diode is 6 volts, and for the second Zener diode at the bottom here is 3.3 volts. The question is find Vout1 and Vout2. Vout1 and Vout2. Next is what is the current through the LED, this white LED. What is the power delivered by the supply? And compare the power absorbed by white LED, this white LED versus 6 volts Zener diode. Now before I go answering this question, just looking at the circuit, okay, first of all, this is Vout1 and Vout2, which are voltages at a point. When it is indicated at a node like this, it means that you want Vout1 with respect to ground. Okay, not across this diode, but with respect to ground. Vout2 is also with respect to ground. Okay, another thing that by looking at the circuit, I have to decide whether this 40 volts is enough to turn on all these LEDs. Alright, so I've redrawn it. Again, when you're doing your solution on paper, redraw the circuit because you may want to label certain things. And as you present your solution, it's easier for your examiner to see what it is that you're referring to, especially for circuits, because you need to put in notations. Okay, so is the voltage positive, the voltage source positive enough to forward bias the white LED and the silicon diode and the Zener breakdown diode VZ1 and VZ2? Okay, to turn on all these LEDs, what you need is 4 volts across the white LED, 6 volts to break down VZ1, 0.7 volts to turn on forward bias the silicon LED, and 3.3 volts to break down VZ2. So that is in total of 14 volts. Okay, but we have 40 volts, 40 volts, so it is enough. So if 14 volts is taken by all these diodes that locks it at 14 volts, where does the other 26 volts go to? It will go to the resistance. The voltage drop will be across the 1.3 kilo ohm resistor. So this resistor here is meant to absorb the extra voltage drop, as well as to limit the current that goes through the LED. So just also by looking at this, since the 40 volts is enough to turn on each of all these diodes, okay, if I want to take V out 2, it will be from this point here above the positive terminal of the silicon diode to ground, which is going to be 0.7 plus 3.3, which is 4 volts, and V out 1, which is going to be here, which is at the negative terminal of the white LED, and it would cover VZ1, silicon diode, and VZ2, because V out 1 is from this point to ground. So that would be 6 plus 0.7 plus 3.3, which is equals to 10 volts. Now if I do Ohm's law, why am I doing Ohm's law? Because I want to know the current through the LED, and the current through the LED, as part of the question just now, the current through the LED is also the current through the resistor, because these are all connection in series. So if I do Ohm's law at the resistance R, I get 26 divided by 1.3K. 26 because that's the voltage drop across the resistor, because the other 14 volts has been taken by the LED, so there's 26 volts left, which is going to be the potential the voltage drop across the resistance. So we have 26 divided by 1.3K, which is the value of R, so we get 20 milliamps. So power of the that is produced by the power supply, that is at the power consumed, is going to be 40 volts times 20 milliamps, which is 800 milliwatts. But the power consumed by the white LED is going to be 4 volts, because that's the voltage drop across it, and the current through it, which is 20 milliamps. So the power consumed by LED is 80 milliwatts, whereas the power consumed by the Zener diode, which has a voltage drop across it 6 volts when it turns on, and it's times 20 milliamps, so I get 120 milliwatts. Okay, and if you look at this, because VZ1, the Zener breakdown voltage, is greater than the forward voltage, 6 greater than 4, whereas the currents are the same, the power consumed by the 6 volt Zener diode is 40 milliwatts more than the white LED. Okay. Alright, so this is an example just for us to see how to handle circuits when there is a Zener diode. So now let's have a look at Zener diode voltage regulator. Introduction. Zener diodes in voltage regulators. Zener diode can be used as a reference voltage and can act as a protection device. Okay, it finds major applications as a regulators. Okay, so what is a regulator? If you say we want to regulate something, it means we want to control something so that it is within a certain value. So a voltage regulator is a system designed, okay, a voltage, I've just drawn a rough circuit here. So I have a Zener voltage regulator circuit here, and it is designed to automatically maintain a constant voltage level for a load. So let's say I have a Zener voltage regulator here, accepting a voltage from a supply, okay, and the supply may have some voltage variations across it, or the load itself may have some different behavior under different conditions, or different loads for different times. But if we have a Zener voltage regulator, it can be designed such that whatever variation you have within an acceptable range of the supply, the load still gets VL, or whatever resistance this load is for whatever different kind of load that we put here, the voltage across it is VL because of the action of the Zener voltage regulator circuit. So there are many applications for Zener diode, but for this syllabus, okay, it's just a simple voltage regulator. The other many applications for Zener diode is such as line regulation, load regulation, voltage regulator, booster. You can do a split supply for single transformer winding, but for this course, we will only consider the simplest form of a voltage regulator as a basic concept. Okay, understanding Zener voltage regulator. So we have, now let's assume we have here a power supply, VPS, and an input resistance. Okay, this is part of the power supply, or this is part of the circuit as well. So we have here a Zener diode connected, and if we look at the VPS, we intend this Zener diode to function in the reverse bias in parallel with RL, okay, which is the load resistance, which will have a voltage across it at VL. So in the diagram, VPS could be the DC voltage power supply, and RN is the internal resistance, RL represents the load. So for this circuit, we want the output voltage to remain constant even when the output load resistance varies over a fairly wide range. Okay, that is what we want. What for this circuit, why do we have the Zener diode connected this way? It's because even though RL may vary, okay, we want the output load resistance, we want the output voltage VL here to remain constant. And again, VPS may have some time varying information, may have some ripple. For example, maybe it came from an AC source that has been rectified by our rectifier circuit that we covered some videos back ago. After that, it goes to a filter, but there's still a ripple. So we do not want that time varying information to disturb the value that we're supposed to deliver to RL. Okay, let's say RL is a load and it is sensitive, and we just want it to receive to be applied with VL. So without the Zener diode, let's say we don't use a Zener diode, we just take the voltage VPS here directly connected to RL, because RL, let's say, needs a DC voltage, so you just take it out and you don't have a regulator in the middle. Now if that happens, the voltage drop across the load RL, which is VL, is highly dependent on the value of RL and VPS as described by voltage divider rule, meaning that if any variation at VPS, VL will show the same kind of variation as VPS linearly because of the voltage divider rule. And VL as well, if it relies only on RL, then it will be Ohm's law, then that will be a linear relationship. So whatever it is that VPS is giving to RL, you're not getting a constant level of power supply. So this would make the voltage across the load not constant. Okay, but we know that electronic circuits needs a constant biasing. So we can add a Zener diode to lock the voltage drop across RL over some range of acceptable RL variation and VPS variation. So we want to have this Zener diode because it will lock the operation. And this is the basic concept of voltage regulator, i.e. when the Zener diode breaks down in reverse bias, it will lock the voltage across the load. Now the resistance Ri here, there is a resistance Ri here. It may come from the power supply, may come from the circuit over here, but it limits the current through the Zener diode and drops the excess voltage between VPS and VZ. So let's say VPS gives 30 volts, but the Zener breakdown is 20 volts, so the extra 10 volts will be dropped across Ri. Also, all this diode, Zener diode, it's important to maintain within power ratings specified. So the R here will limit the current through the Zener diode. Okay, so we are now ready to do voltage regulator circuit analysis. So for the purpose of this course, we will consider circuit analysis of the Zener voltage circuit for the following cases. We know that there are a whole range of diode applications. It's a very useful device, okay? But for our course, we are just going to look at this Zener voltage regulator here, and we're going to look at the simplest form under the situation of 3 cases. The first is if we already know a specific value for Vin and a specific value for RL. The second case is we know that the voltage regulator is intended to be able to tolerate a range of RL. So we want to find what that range is. So in other words, we assume a fixed Vin and a variable RL, in the sense that to see the range of RL, that the voltage regulator can work while maintaining Zener diode ratings. So what is RL minimum and what is RL maximum when we fix values for Vin, Rin, and Vz. Okay, so case 3 is again earlier just now we mentioned that we want to the voltage regulator is so that the voltage across RL can tolerate changes across the changes in the input supply and the input voltage. So we would like to know what is the range of Vin maximum to Vin minimum to Vin maximum when the values Rin, RL, and Vz are all set while maintaining Zener diode ratings.